The next session is called Applied Mineralogy as a Tool to Research the Provenance and Technology of Ancient Ceramics. Many of you probably do not know that the study of ancient ceramics in the U.S. actually started here at Carnegie in the 1940s and 50s by two women scientists, Anna Shepard, who looked at the petrography and did refiring studies of Southwest pottery, and by Marie Farnsworth, who studied classical Greek pottery using X-ray diffraction, atomic absorption, and other trace element techniques. In 1952, Homer Thompson, who'd been an archaeologist excavating the Keramikos near the Parthenon in Greece, organized, after whom Indiana Jones was modeled quite appropriately, down to the hat, organized a meeting at the Princeton Center for Advanced Studies with Libby of C14 date, fame, Sayer, Brookhaven, who developed INAA, and others to propose how to apply science to archaeological and art objects, given the constraints of sampling, for instance, preferable use of NDE techniques, to study variability, to reverse engineer ancient pyrotechnologies, to determine rate-limiting steps in processing that oftentimes are skewed in distribution as you run up against materials constraints, and that actually can be extrapolated and interpreted to get at decision-making and behavior of ancient peoples. So with this in mind, we're going to have two papers today. They're going to be in inverse order as they're listed in the program. The first is going to be by Gilberto Artioli of the Department of Geosciences at the University of Padova. Modern Mineralogy in Ancient Pots, the Archaeometry of Ceramics, and the second by Michael Tite of the Research Laboratory for Archaeometry and the History of Art at Oxford University, and the former head of scientific research at the British Museum. And his talk will be called The Mineralogy of Opaque Ceramic Glazes, Development in the Islamic World and Europe from the 7th to 16th centuries Christian era.
Right, well, first of all, thank you very much for inviting me. I should point out that I'm not a mineralogist. I'm a physicist by training, and I haven't actually done any serious physics for the last 40 or more years. I've been applying my knowledge to studying the production technology of ancient ceramics. And on the way, I've learned a bit of mineralogy, but I'm not a mineralogist. This afternoon, I'm going to talk about a specific type of glaze which was used from the 7th to the 16th century, opaque glaze, as a specific case study of some of the sort of overview that my previous speaker has provided. Now, can I get this to work? No? And this is the pointer, is it? Yes, brilliant. Right. Well, our story starts with the production, or the story of opaque glazes starts with the production of glass in Egypt in the Near East around 1500 BC. And there you have lead antimonate is used to produce an opaque yellow glass, which you can see on this vessel here, perhaps in imitation of gold. Calcium antimonate is used to produce an opaque white glass, again seen on this ancient Greek vessel here. Again, perhaps in imitation of silver. And the particles, the lead antimonate and calcium antimonate particles, scatter the light and result in an opaque glaze, or opaque glass in this case. Now, these antimony-based opacifiers continued to be used until the Roman glassmakers switched around 400 AD to use tin paste opacifiers, lead stannate for the yellow, and tin oxide for the white. And these opacifiers continued to be used by Byzantine and Islamic glassmakers. Now, coinciding with the beginnings of glass production, you have the first glazed ceramics being produced in Mesopotamia. Here you have an alkali lime glaze, about 18% alkali, 6% lime. These are transparent glazes, colored blue or turquoise with copper. and the glazes were possibly produced by using ground-up transparent glass, applying it to a biscuit-fired clay body, and then refiring it to produce a glaze. And this type of glaze continued through into the Islamic period. And then around about 100 BC, Roman potters introduced a very high lead glazes, about more than 60% lead, less than about 2% alkali. These were again transparent, and they continued in use by Byzantine and Islamic potters. So turning now to the real subject of this lecture, which is the opaque glazes, except for glazed bricks produced in Mesopotamia around the first millennium, the first opaque glazed ceramics were produced in Egypt and Syria in the late 7th, early 8th century. The opaque yellow is achieved by producing a type 2 lead stenate, which is PbSnO3, in a very high lead glaze, again. Now, this type 2 has some silica substituted for tin, so that in the PbSnO3, the tin to silica ratio in the SM part is typically in the range of 5 to 10. And as a result of the incorporation of the silica, the orthorhombic form of lead stenate, Pb2SnO4 type 1, is converted to this type 2 form, which is cubic, and produces a more definite yellow color. So that's a yellow glaze we're looking at. The white glaze is produced by tin oxide in a high lead alkali glaze, some alkali in this, less lead, more alkali. And again, the ratio of lead to tin is in the range 16 to 50 for the yellow glazes, and from 4 to 7, that ratio for the white glazes. And again, the lead stenite and the tin oxide particles scatter the light, resulting in opacification. And this just shows some SEM cross-sections through some of these glazes in backscattered mode, so that high atomic number phases show up much brighter. And you can see here, this is a yellow glaze from Syria, and if you're close enough, you can see particles of lead stenate in this. In this glaze from Iran, a yellow glaze, shows the yellow there, much more well-formed and larger particles of lead stenite, producing the opacification. Then this is a white glaze from Syria with a mass of small tin oxide particles showing up white. And this is a white glaze from Iraq. Again, white particles of a tin oxide, and also some opacification provided by particles of quartz in the glaze. Now, the motivation. This shows a typical, I've done it as I knew I would. There we are. This shows a typical yellow glazed vessel from Egypt around the 8th century AD. And we think the motivation for production of these yellow glazed ceramics was to replace the African red slipwares, and this is an example of African slipware, which was a fine class of ceramics, because the supply of the African slipware had dried up as a result of the destruction of the kilns in North Africa by advancing Arab armies. The technology for production of this sort of ware, I think, can be explained by the interaction between potters who were using very high lead glazes, and glassmakers who were using lead stenate and tin oxide. So, as with much technological development, it's a result of interaction between different technologies. So, how do you produce these opaque glazes? Now, the ancient texts, there's one around 1300 by Abu Qasim, suggests that to produce the yellow and white glazes was a two-stage process. And the feasibility of this two-stage process we've confirmed by laboratory replication. First of all, you take mixtures of lead and tin metals, and in our experiments, we use the ratio of lead to tin, naught, so just tin, and then lead to tin, 7 and 30. You calcine them at temperatures in the range 600 to 800, and if you've just got tin, you get a white calc, an oxide powder. If you've got lead and tin, a ratio of 7 and 30, you get a yellowish calc, a powder, oxide particles, powder, as you see here. X-ray diffraction indicates, because of the absence of silica, the yellow in there is due to type 1, lead stenate, Pb2SO4, as well as some tin oxide. Then, as the second stage, you take some of this ground calc mixture and then mix it with either silica or silica plus alkali lime frit. You apply this mixture to a biscuit-fired body and then refire the whole thing to either 800 or 950 degrees. At least this is what we did in the laboratory. And the next picture shows you some of the glazes we produced. So our first group of glazes were produced by firing at 500 up here. And the first glaze is silica plus lead tin ratio, calc of a ratio of 30. You get quite an intense yellow glaze. The second one is again silica, but with a lead tin ratio of only 7. You're still getting a yellowish glaze. But if you take a mixture of silica and some frit, which is some alkali, and this same ratio of lead to tin, you get a white glaze, tin oxide. So you're using the same calc, but actually mixing it with silica or with mixing it in frit. If you fire to a higher temperature, which is shown here, at 900 for the first glaze, you actually get a rather browny, glassy mixture with no tin particles surviving. And for the second two glazes, you get this slightly glossy white glaze with tin oxide opacification. And this switch from lead stenate to tin oxide at higher temperatures, we followed with high temperature XRD, where you take a mixture and heat it up progressively at quite a slow rate. And you can see that, first of all, you get the formation of type 1 lead stenate, Pb2 SN04, and then you get the type 2 PbSN03 coming in at about 600, and then eventually, at this slow heating rate, you start getting the recrystallization of tin oxide at 700 or 800. And so this is where you get this switch from the yellow to the white if you increase the firing temperature of mixture. So what I now want to do is to investigate the spread of these glazes beyond Egypt and the Levant, where they start. So the high lead yellow glaze and the high lead alkali white glaze spread from Syria and Levant into Mesopotamia by around the 8th century. And this spread was probably associated with the move of the Abbasid capital from Damascus to Baghdad in 762. In addition, in Mesopotamia, you get a second white glaze, and this is a cross-section through it, again opacified with tin, but this is an alkali, essentially an alkali glaze with just a small amount of lead, and tin ratios quite low. And we think this technology is derived from the Islamic opaque mosaic glass makers. This is an example of mosaic Islamic glass of around the beginning of the 9th century, where you've got white and yellow, and they were using the white is an alkali lead-type glass with a similar PB to tin ratio as in this white glaze up here. In Mesopotamia, it's generally argued that the white opaque glazes were produced in response to the import of Chinese porcelain. And this is a sample of Chinese porcelain of the type but was being imported into Abbasid, Iraq at the time. And since they didn't have a white firing clays to produce something white like that, they made use of the tin opacified glaze. Also, the tin opacified glaze provides the ideal background for the cobalt blue decoration, which the Islamic potters produce, an on-glaze decoration, and also the right background for lusterware decoration, which emerged in the 9th century, and this is a luster decoration plate. From Mesopotamia, the high lead yellow glazes spread into Iran, into Central Asia, Samarkand, and eventually in the Middle Ages down into India, the yellow glazes. But eastwards from Mesopotamia, which is in this sort of area here, the yellow glazes seem to have fallen out of use, except in Egypt down here, where they introduce a lead antimonate yellow glaze, but that's another story. As far as the white glazes are concerned, they do spread to a limited extent further eastwards, but they continue to be produced extensively in the Levant and Syria. They spread into Egypt, and they spread into North Africa, and also into Islamic Spain. Egypt is the basis, I think, for the spread to North Africa. And then the next step is when they go beyond the Islamic world, either from Islamic Spain or from North Africa, they spread into the white glazes, lead alkali tin oxide white glaze technology spreads into southern Europe by the 13th century. And then with the flowering of Italian MAIOLICA in the 15th century, this is of particular note, and I'll come back to that briefly in a moment. Then in the 17th century, you get the spread of the same tin opacified technology spreading into Northern Europe, and you see it in France, Netherlands, Germany, and England, where it's used to produce Delftware and faience. And this is an example. This is an example of Italian MAIOLICA, the 15th century. This is an example of Delftware from the Netherlands of the 17th century. And so tin oxide as an opacifier is the principal glaze opacifier right into the 19th century, and into the 20th century it's used by craft potters. In the 19th century, commercially, it's replaced by titanium and zirconium compounds as opacifiers. And then finally, I want to say something about Italian MAIOLICA, and specifically the Italian MAIOLICA referred to as Istoriato, which was decorated with complex painted scenes, such as you can see here on a plate, and tended to be produced from about 1480 to 1560, and it represents the top of the Italian MAIOLICA range. This is a cross-section through a MAIOLICA body. You've got the body here, and the body of MAIOLICA is produced using a calcareous clay, containing 15 to 25% of lime. It was biscuit fired to about 900 to 1,000 degrees, which results in a body of a buff color. And then it's glazed with a lead alkali glaze, and you can see that here, opacified with tin, but it also contains quite a lot of particles of sand, which makes this glaze much more robust, because you're in fact going to apply on top of the glaze a range of mineral pigments to decorate the ceramic and finish up with something as elaborate as that. And the colors you use: cobalt for dark blue, copper for turquoise, manganese for purple, and also you're using lead antimonate, again as an opacifier. And here you can see a region of the yellow glaze where you've got the lead antimonate particles surviving to produce the yellow color. And so one's reverted back at this stage definitely to the use of lead antimonate, as was used 1500 BC for glass. And then sometimes you cover your glaze, the pigments with a transparent layer of higher lead oxide, referred to as coperto. This has a lower viscosity, so it diffuses into the in among the pigments and into the glaze and gives a bright, smooth, reflective surface. And then the whole thing is fired for a second time. I'll admit that IZNIK ware is the artistic peak of Islamic ceramic production, and one can see some of the pieces there, first produced again in imitation of Chinese porcelain. So Chinese porcelain has quite an input and influence on the developments of ceramics in the West. And of course, there's a story in Europe as well, which again is another story of the import of Chinese porcelain and the development of various European porcelains. So finally, I think I want to acknowledge the debt to the following colleagues and collaborators over the years, without whom I could not have produced this paper. In particular, one of my most recent of my DPhil students, Dr. Moujet Matan, who was then is now a postdoc at Oxford University, and then Professor Trinitat Pradel and Dr. Elena Selenis from the Polytechnic University of Barcelona, and Andrew Shortland, who's professor at Cranfield and another of my ex-students. So thank you for your attention.